Oh, hi. Welcome to part C of chapter 6, gases. In part C, we will look at section 6.8, 6.9, and 6.10. This is a short session. Please have a pen and a paper. There will be some mock example I'll go through, which you'll use the same equation in the quiz and the upcoming midterm exam. In section 6.8, collect kinetic molecular theory of gases. What is kinetic molecular theory of gases? This is a theory or a model which explains the macroscopic behavior of gases. It's a model which explains the microscopic what we see, and it is used to explain the gas laws. We'll see later on how this model has been used in explaining the Charles law, Paul's law, and Avogadro's law. Simply, it's the simplest model. And in this theory, a gas is modeled as a collection of particles. Look at the container here, the blue spheres. It's moving randomly in a closed container. This is just like a sample of a gas used to explain the kinetic molecular theory of gases. You need to know the postulate. We have what we call the postulate or assumptions, which makes up the kinetic molecular theory. And these are the postulates. It's assumed that the size of the gas molecule is negligibly small compared to the volume of the container, In other words, if you think of the volume of this container compared to the volume occupied by the actual molecules or atom of a gas, it is negligibly small. The average kinetic energy of particles is proportional to temperature. That means if you increase the temperature, the kinetic energy of the gas particles or molecule will increase as well. There is direct linear relationship between kinetic energy and the temperature. Remember kinetic energy, we're going to talk about that in chapter 7. It is the energy possessed from intro to chem. Kinetic energy is the energy possessed by moving object. Energy is motion. And in this case, we are relating the temperature and the energy of the moving particles. Postulate number 3 says that the collision of one particle with one another or with the walls of the container is completely elastic. That means it doesn't stick together. That means as the particle hit the wall of the container, it bounces back. For example, if you see here, this particle may have pumped into the wall and it is bouncing back. It's not sticking on the wall. Or when they collide, you see this molecule and this molecule is colliding somewhere here, and they don't stick to one another. They bounce back, and that's what is meant by that the particles, the collision is completely elastic. These are just continuation of the postulate which make up the kinetic molecular theory, talk about the particle size, attraction between particles is negligible. That means they don't come to one another. When particles move, it hit one another as gas particle or container. They do not stick, is what I was talking about. But they bounce off and continue moving in different directions. They move randomly. Or there is a lot of empty space in between the gas particle. This is 1, 2, 3, 4. There are 4 postulates. So here, the last one, there is a lot of empty space between the gas particle compared to the size of the particle. So the empty space illustrates the compressibility of the gases. You can compress because there is large intermolecular spaces between the particles. If I go here, if you think about the space between this particle and this particle, this is so large compared to in solids and liquids, compared to solids and liquids. So remember, you can make your own notes, write the four postulates which makes up the kinetic molecular theory. I've seen question in the exam asking which one of the following is not, all right, the postulate in kinetic molecular theory, or which one of the following is. You need to know the four postulate, the four assumption which makes up the kinetic molecular theory. And remember, where we are going with this is explaining the Carr's laws we use, all right? We use kinetic molecular theory to explain the Carr's laws, which we are going to look at it later on. So average kinetic energy of the particles is proportional to temperature in Kelvin. Remember how to change temperature from degrees Celsius to Kelvin, adding 273, which explains why when you raise the temperature, the speed or the average speed of particles also increase. But not all Carr's particles move at the same speed because of the molar mass. They are not the same, so it's going to change, or they don't have the same speed because of that. Remember, kinetic energy is equals to half mv squared, where m is the mass. And of course, if you think of hydrogen gas and krypton gas, for example, they have different what? They have different masses, and therefore their kinetic energy cannot be the same. All right, let's see if two gases, for example, here collide, their collision is elastic. What we mean by elastic is they bounce back. It looks like someone was playing pool table, similar way. When they collide, this will go different direction. But in elastic collision, two objects stick together after the collision. So elastic versus inelastic. This is what's happening when two Carr's particles collide, their collision is completely elastic. Even if they bump onto the wall of the container, still the collision is elastic. So remember, elastic versus inelastic. The bouncing on the wall of the container leads to Carr's pressure, okay? And pressure is the ratio of the force exerted by the Carr's particle on the wall of the container is the ratio of the force over area, of which if we have so many particles, this will result in large force on the surface, on the wall of the container, and therefore the pressure will increase because of what? Because of the constant moving and pumping on the wall. The more we have many particles, they create the pressure. They create the pressure. Let's see how we can relate the kinetic molecular theory with the Carr's laws, which is Charles' law, Poyle's law, and Avogadro's law. And starting off with Poyle's law, explaining using the kinetic molecular theory. This is Poyle's law, states that the volume of a gas is inversely proportional to the pressure of a gas at a constant number of particles and temperature. So temperature is constant, number of moles is constant. So if you recall the four parameters, pressure, volume, temperature, and the number of moles, this is what is changing in Poyle's law. And because of the decreasing the volume forces the molecule into a smaller space, all right? And therefore, the molecule will pump into each other, will pump into the on the surface of the container, on the surface of the container. This is what is explained here, that reducing, let's say, for example, here I have this container and two molecules right there. Chances of pumping into one another is compared to this, all right? If I have a small one here with the two particles in there, this will be high pressure, this will be low pressure because of constant moving. If it's moving in that direction, moving in this direction, this one will pump on the wall many times compared to when we have a large volume. This is large volume, and this is a small volume. And using kinetic molecular theory of particles moving randomly, this explains why we see when you decrease the volume in Poiseuille's law, the pressure will increase. When you increase the volume, the pressure will decrease. The pressure will decrease. This is using the kinetic molecular theory of gases moving randomly. Now, more molecules will collide with the container at any instant because of what? Because of the small volume of the container. Now, for Charles' law, all right, Charles' law states that the volume of a gas is directly proportional to absolute temperature at constant number of moles and pressure. N is constant and pressure is constant, which according to kinetic molecular theory, when you increase the temperature of a gas, the average speed here, all right, increase. Remember when we were stating or looking at the Charles law, we didn't explain why, but now kinetic molecular theory is explaining the reason why you increase the temperature, the volume increases because of average speed, and thus the average kinetic energy will increase. It will, all right, it will expand and the volume will increase. So if I have a gas, all right, low temperature, and then gas will expand high temperature. So here the volume will increase as you increase the temperature because of the average kinetic. So here, this will have high kinetic energy, energy. Here is low kinetic energy or average kinetic energy for gas particles. So the greater the volume, spreads out the collision out over a greater surface area, so the pressure is unchanged. The pressure is unchanged with that. Now, Avogadro's law, remember Avogadro's law states that the volume of a gas is directly proportional to the number of what? The number of gas particle. N is directly proportional in Avogadro's law. Volume is directly proportional to N, where N is number of gas particles. You can feel particles or moles. Say moles is the same thing, and say gas particle or moles. From kinetic molecular theory of gases, increasing the number of gas molecule causes more of them to hit the wall of the container at the same time, and therefore the pressure, to keep the pressure constant, the volume must increase. The volume must increase. I want you to take note of how the kinetic molecular theory, which says that increasing the number will cause more of them to hit the wall, because from the kinetic molecular theory, gases or gas particles move randomly at a constant speed, and the more you have, the more will come onto the wall of container. And to have it constant, the volume must increase. The volume must increase to keep the pressure constant. Now, Dalton's law, which states that the total pressure of gas mixtures is the sum of the partial pressures of individual components. Remember Dalton's law of partial pressure. All right. Assume this P total. All right. P total equals to P of gas 1 plus P of gas 2 plus, depending on how many cars you have in a sample of a cars mixture, the total pressure is equals to the sum of all partial pressure, where P is the partial pressure of cars 1, cars 2, and cars 3. And the reason, according to kinetic molecular theory, the particles have negligible size and therefore do not interact. Particles of different have the same average kinetic energy at a given. So this what explain why when you see or when you have total pressure, the sum of each one of them based on different masses, they have same average kinetic energy. Because of that, the total pressure of the collision is the same. So let's see the molecular velocities and why gases have same average kinetic energy, even though we have you may have different type of gases, but we say average kinetic energy for all of them. If a different gas mixtures, if they have different masses, the only way for them to have same kinetic energy is to have different average velocities. We call it root mean velocity. And to account for that, for all of them to have average, even though they may have different masses, there is an equation here. It's beyond the scope of this course how the three came into the picture. This is stand for root mean speed, all right, or average speed. Note that this UR, let me just minimize this. I'm writing something on my whiteboard. This is RMS. This stands for root mean velocity, or sometimes root mean speed, average speed of gas particle. And for that to happen, you need to understand the equation, what it stands for, and what it means. This is root mean. It is the square root of, all right, square root of, this is square root of 3RT over M here. Let me explain what this stands for. This stands for molar mass of gas, molar mass of gas in kg. So you need to change the mass to kilogram. I'm going to explain to you why you need to change the mass to kilogram. R is the universal gas constant. R is gas constant. And remember, there are three values. It's not five values. It's not the same as the R we know. It's just 8.314 joules per mole per Kelvin. This is the unit of R. It's not the R I used before. And here is the temperature in Kelvin. Temperature in Kelvin. You need to change the temperature in Kelvin. Temperature Kelvin. So from this, you can calculate the root mean velocity of a sample of a gas using this equation. This is just the constant. Probably maybe looking at a worked example on how to calculate the root mean velocity of a sample of a gas. All right, root mean velocity. This is what I was explaining, the constant since we are talking about kinetic energy, this is the value for R. Whatever you are handling or calculating energy, you'll see in chain chem 2, where R, you can use this value. And the other value we looked at before in ideal gas equation for energy. 1 joule equals to 1 kg times meter square per second square equals to 1 joule. We want to relate the mass to the energy. Remember kinetic energy here. Therefore, this explains why I say the mass has to be in kg. Remember here, I say molar mass has to be in kg, molar mass of a gas. So here, because we are calculating energy, you need to change the molar mass into kilogram. Here is an example on how to calculate the root mean velocity. Please be assured you'll see this in the next quiz exam, how to calculate, or I'll ask you how to calculate the root mean square speed or velocity of a sample of a gas. Anytime you see RMS, it is stand for root mean square speed of a molecule in a sample of nitrogen gas. Remember, behind the scene, you are expected. Remember, I said temperature has to be in Kelvin. You should be able to calculate the nitrogen. Sometimes you may be given nitrogen gas, no gases except for group 8 are diatomic. Oxygen gas is O2. Hydrogen gas is H2. Nitrogen gas, in this case, is H2. Chlorine gas Cl2. So all gases are diatomic, and in this case, do not use the 14.01 on the periodic table. You have to multiply by 2. It's assumed that you know how to write the formulas given the names. So what we need to do is plug in the equation. This is what you need to remember in calculating the root mean square velocity. Since we want to calculate energy, we convert this to kilojoules, and that is why we have here kilogram from joules. All right, 8.31 meter square times 10 to negative 3 for kilojoules. So here, this is the R value, okay? And the temperature in Kelvin, remember what I said, temperature has to be in Kelvin. 298 comes from changing the 25 to absolute or to Kelvin, adding 273. This is the molar mass of nitrogen gas in kg. You should be able to convert the mass into kilogram into kilogram. And this one also, we change the mass into kg. Look at this relationship. I know this is given, but how do we end up with that? It's based on what I covered earlier on here, that 1 joule, since 1 joule here is the same as kg, it's just the same value, same numerical value, because moving from here to here, because 1 joule is the same as this. That's why we have this value. We didn't change anything. It's just, and this is the root mean speed for gases. Remember, we're looking at the velocities of gases in relation to the temperature. To wrap up the root mean square, how to calculate the root mean square velocity of a sample of a gas. Remember to change the temperature to Kelvin. 3 here is a constant. Please remember that. And the molar mass has to be in kg. At the end of the semester or even in the upcoming quiz, please remember there will be 2 values for R. When do you use this? And when do you use the other one? 0.08206, all right? When do you use that? You got to practice, know when to use the given value for R here. Please look at problem number 91. 92 on page 258 on how to calculate the root mean square. Let's see the learning check here. If we are asked what is the root mean speed for an atom in a sample of helium. Helium, atomic mass of helium, right? Atomic mass of helium. Of the periodic table, all right? Helium is in group 8. It's not diatomic. And this will be 4.00 grams, which is the same as 4.00 times 10 raised to negative, all right, negative 3 kg. I just changed that to kilogram. Remember to change the mass in what? Mass in kg. Note. Molar mass in kg, which is this one right here. Molar mass in kg. So that when we plug in the equation, R, remember R is 8.314 kg meter square square. That's what we're going to use. And temperature in Kelvin is given by 25 plus 273, which is 298. Remember to change the temperature to Kelvin, temperature to Kelvin. So if we plug in now, root mean speed is given by the square root of 3 R T over molar mass. This is the molar mass of helium. And remember in kg, if I plug in that, it's going to be the square root of 3 times 8.314, all right, kg meter square times 298, okay, over 4.00 times 10 raised to negative 3 kg times 2, this is negative 3. So what I do have here, it will give me the root mean square. Make sure you know how to use the scientific calculator. I will enable the scientific calculator on analog 6 times 10 raised to 3 meters per square. This is the root mean velocity or speed for helium gas at 25 degrees Celsius. So remember, if we increase the temperature, this value will go up as well. Like I said, look at page 258, problem 91 and 92. It asks you to calculate the root mean speed of a sample of a gas. Let's see molecular speed versus the molar mass. All right. The speed is related to, the point here is the speed is related to molar mass. To have the same average speed or kinetic energy, heavier molecules must have a slower average speed. What does that mean? It's because if you remember the kinetic energy is K E is given by a half mv square. So for a heavier molecule, mass here in kg, this is the mass in kg, whereas this is velocity, the speed in meter per square. This is the speed in meter per second. So the statement here is if heavier molecules to have the same average kinetic energy, heavier molecules have to move at a slower speed, whereas lighter molecule will have to move at a greater speed to have the average. So from this, with this understanding, the diagram here illustrates that point. If you look at hydrogen gas, it is way lighter than helium, all right? Compared to 18, this is around 2.2 grams. This is 4 grams. This is 18.0. This is 28. And this is 32. And this is 32, which explain for all these to have average. If it is in a closed container to have average kinetic energy, it has shown this. Now, with this understanding, to have same speed, a question in exam will be arrange the following according to increase in kinetic energy or in decrease in kinetic energy, or which one of the following will have same kinetic energy. It is just a general understanding that from the equation for calculating kinetic energy, heavier molecules must move at a slower speed. So you see here molecular velocity. Velocity is the same as the speed, and heavier molecule will have at a slower pace or slower speed compared to lighter ones so that they can have same or average kinetic energy. I will not ask you to calculate the kinetic energy, but it's conceptual question that arrange according to increase in velocity. So this is according to increase. Going this way or increase will be, decrease will be, increase will be in this. This is according to increase. This is low, this is high because of average to end up with kinetic energy. Here is a question or conceptual question on the same. If you are asked at 333 Kelvin is the temperature, which one of the following pairs of gases below will have most nearly the same identical rate of evolution? Evolution is movement of particle through a hole. We'll see momentarily the difference between diffusion and evolution. But before that, this is just, to evuse is to move. So here we are looking at this problem in terms of velocity. And from the previous slide, we look at the speed versus what? The molar mass. Therefore, in order for you to make a conclusion, you need to calculate or look at the molar mass of each of these gases. And with that, if I just real quick in A, dinitrogen dioxide and nitrogen dioxide. B, here we have carbon monoxide and nitrogen gas. This is carbon monoxide. C, we have nitrogen gas and two, and oxygen gas like that. D, there is carbon monoxide and carbon dioxide. E is N, nitrogen dioxide and N2O4. So here, if I look at remember, heavier molecules or particles move at a lower speed to have the same average kinetic energy. Rate of evolution, moving with the energy. So this will have, or this is 28.002. This is 32. I'm looking at the atomic masses. This is grams per mole. This is grams per mole. This is 46.013. Is it 40? No, 28. This is 28. 0, 1. And this is 28.013. This is 28.013. And remember grams per mole. This is grams per mole, grams per mole. And this is 32.00 grams per mole. This is 28.01. This is 44.01 grams per mole. All right, per mole. And this is 46. This is 46. I meant to say this is 40. This is 46.0. And 2. Nitrogen dioxide. We have 28, let's say 28.0 2 plus 16.00. This is 4. It is 44.02. This is 44.02 grams. 44.02 grams. This is 90. 46.01, and this is 92.011 grams per mole. The point here is the molar masses. What I do have here, molar masses of each one of them. And to make a conclusion on side question, you have to look at which pair has almost the same molar masses so that they will move at the same speed. If I look at B, this is 28, and the correct answer is B. This one, they are varying atomic or molar masses, which means they will have different speed. Please look at page 258, problem number 27. It will just walk you through. Please look at the solution at the back of the text on the rate of evolution and how you can qualitatively come up to a conclusion, which one will move faster, which one will move slower. You may be asked to rank according to increase in velocity, according to decrease in velocity, and this has to do with just the general understanding of molecular speed versus molar masses So moving forward, the temperature also affects, all right, the speed. If you look at the same cars, all right, at the same temperature, they move, they have average. So same cars here, looking at the velocities as a function of temperature. The higher the temperature, the greater the velocity, all right? The greater number of increasing the temperature, increase the velocity. Simple as that. Now, there is the evolution and diffusion. Of course, here, if we look at diffusion, conceptual question, which of the following, which sample of an ideal gas has the greatest pressure? Assume that the mass of each particle is proportional to its size and that all gases or all the gas samples are at the same temperature, Remember what we say as far as the greater number of particles, the greater the pressure, and the answer here is C, because we have greater number of particles. This is relation to same temperature, same size. The greater number, they will have great pressure. Let's see. Section 6.9, sorry, mean free path diffusion and evolution. I know in the last slide I mentioned evolution and you didn't know what it is. was the first time, but we will define evolution and diffusion in a moment. But what is mean free path? Mean free path is the average distance a molecule travels between a collision. We call it mean free path. When it collides, what is the distance between one collision to the other? As the mean free path decreases as the pressure increases. So you can imagine if we decrease the volume of this container, if we decrease the volume of the container, more or there will be more collision. Gas particles, gas molecule in this container, we decrease the volume, will travel less distance to make a collision. So average distance a molecule travel between each collision is called the mean free path. There is a diffusion and evolution which you need to understand. The process by which gas molecules spread out from high concentration to low concentration is called diffusion. Remember, in the text, the author talks about someone using the air freshener in the bathroom, and it will take a while before it travels to your nostril. It's because the particles do not travel straight. It just travel randomly. And the process by which gas molecules spread out from high concentration to low concentration is called diffusion. Compared to evolution, which is the movement of gas particles through, you have to remember this, underline the word through a small hole into a vacuum. We call it evolution. There's a difference between evolution and diffusion. We'll see in Count's law how to calculate the rate of evolution. Rate of diffusion and evolution of a gas are both related to root mean square, which we talked about in the previous couple of slides behind. Please go back again and revisit the root mean square. Velocity for gases. So for gases at the same temperature, this means that same rate of gas movement is inversely proportional to square root of their molar masses. We call this the Count's law of evolution. Before we look at that, this is just the parallel, drawing a parallel between evolution, which is the escape of gas molecule through a tiny hole. You see, this gases is effusing through a small hole here into a vacuum. There's a vacuum. Whereas in diffusion, it's just movement of gas from from high concentration to a low concentration. Back to rate of evolution. Count's law states that for two different gases at the same temperature, the ratio of their rate of evolution is given by the following equation. We call this Count's law of evolution. And remember, evolution is the escape of gas molecule from or through a tiny hole into a vacuum. And their rate of evolution is proportional or inverse proportional. We talk about inverse proportion here. Inverse proportion. That is why this A is A. This is the rate of A, rate of B, the molar mass of A, the molar mass of B. You see this relationship? We call this inverse relation. The M is the molar mass of A. All right, rate of A, and M stand for molar mass. So if I can rewrite the equation here, sometimes you may think that what is rate A over rate B equals to the square root of molar mass of B over molar mass of A, of class A. Everything is under the root. What I want to show you here is 1, 2, 3, 4. If you know 3, you can calculate the fourth one. You can be asked what is the ratio of their rate of evolution. If you know, if you are given the name of gases, for example, say helium and krypton, you can look at the periodic table to determine their molar mass. Or if it is nitrogen gas and hydrogen gas, remember some gases are diatomic, some are atoms such as in group 8, you will have to plug in here. You don't need to change to kg, just like I said previously. So if you are asked to find the molar mass, you will have to find the square. Look at this. So if I square both sides, right? Rate of A over rate of B class B. In that case, let's use uppercase. If I square this, equals to molar mass of B over molar what? Molar mass of A. The reason why I'm bringing this to equation here is from Cramp's law is you can be asked to calculate the molar mass of A given the left side of this Cramp's law. These are the molar masses. From here, you can either find the molar mass of B, molar mass of A, if you know the information on the right side and on the right left side. We'll see one example. Here is the learning check using the Cramp's law. This is what you expect in the exam. Find the ratio of evolution of hydrogen gas and krypton hydrogen gas. So ratio will be rate of hydrogen gas over rate of krypton gas is given by the square root of molar mass of, this is krypton, AR, over molar mass of, is it helium? It's hydrogen. Yes, it's hydrogen. Hydrogen, H2. Remember, it's the atomic. So what we need to do here is include the, all right, look from the periodic table. Sorry about that. I was just writing what the problem here, rate of hydrogen gas over rate of krypton gas. Krypton is not the atomic of the periodic table. You should know that. So here is the square root of 83.80 grams per mole. This is for krypton over 2.02 grams per mole. You'll end up with 6.44. All right. This is the ratio of rate of evolution. I'll look at problem number 93, 95 in the text. Practice with those. Every time I solve a problem, I give you or lead you to where you can practice as well. Know that you know the material. You don't get stuck in the Alex assignment. All right, Alex assignment. So this is Cramp's law. Do more practice on that. Lastly, on page, chapter 6, this is the last section, last item I would like to cover. Real gases. What is real gases? There is real gases versus ideal. Ideal gas actually does not. It's just an assumption that ideal. For example, if we say ideal, that means gas molecule do not occupy anything. But we know in reality, hydrogen gas, they are particles and they occupy the form. So a ideal gas satisfied all the postulates we said earlier on, but in reality, real gases do not follow the ideal. We'll see that momentarily. Real gases such as hydrogen gas, helium gas, do not behave like ideal. do not follow the ideal equation. Underline at high pressure and low temperature, all right, real gases deviate from ideal. At high pressure and low temperature, real gases often do not follow the ideal equation. We'll see that momentarily. Remember, ideal gas law assumes that no attraction between gas molecules, but in real gases, there's attraction between molecules. There's no way molecules do attract. Gas molecules do not take up space. You see this, you say, we assume that, they do not take up space, but we know in reality, if there is small particles, it will still occupy some space in a container. Remember what I used to circle in there? Since still some space will be occupied by gas particles, gas molecule, and based on the kinetic molecular theory. So here at low temperature, high pressure, low temperature and high pressure, these assumptions are no longer valid for real gases. Look at the ideal gas. All right, ideal gas at STP occupies 22.41 liters at STP. Remember what we say, and we are talking about the 1 mole of ideal gas. But these are real gases: chlorine gas, carbon dioxide gas, ammonia gas, nitrogen gas, helium gas, and hydrogen gas. If you look at this, it's deviating from what? From the ideal. These are called real gases. At STP, it's 22.42 instead of 22.41, 22.06 instead of 22 at STP. You see this? They are not, except for helium right here, which matches exactly, but there's deviation from what? There's deviation from ideal. We see that. Why? Why is it deviating from ideal? It's because at lower pressure, the molar volume of argon is nearly identical to that of ideal. We'll see comparing effect of Vinite volume. And we're using here argon as an example to illustrate deviation from what? Deviation from ideality. So at low pressure, molar volume of argon is nearly identical to that of ideal gas. But at higher pressure, we'll see what will happen. But as the pressure increases, the molar volume of argon becomes greater than that of ideal. There's a diagram which shows that for argon, if you look at the pressure, as pressure increases, argon deviates from ideal. The red diagram here indicates ideal gas. And if you look at the low pressure, argon and ideal gas behave the same. So real gases at certain condition at high pressure and low temperature, because of the real molecules taking up space, the molar volume of gas is larger than the predicted. Now see that prediction. So in order to calculate the pressure of real gases and volume of real gases, we have what we call van der Waals equation, all right, which we use to calculate the pressure for real gases. And we'll see that, which is a modification of what? Modification of ideal. I've illustrated from that diagram that ideal gas or real gases do not behave as ideal gas at low temperature and high pressure. There is some deviation. And how do we really account for, the actual pressure? We use what we call van der Waals equation, all right, to calculate the pressure. Van der Waals was, and van der Waals equation is used to calculate the pressure. And volume for what? Real gases. Remember ideal gas equation? That's for ideal gas. But van der Waals equation is used to calculate the pressure or volume of real gases. There's some modification here, all right? Based on Van der Waal, there is some modification for volume correction. There is the pressure correction and the volume. So Van der Waal modified the ideal gas equation to account for the molecular volume. Molecular volume is the volume actually occupied by the gas molecule. And B is called Van der Waal constant, and it is for volume for real gases. It is given by number of moles times the universal gas constant, which is 0.08206, times the temperature in Kelvin over pressure in atmospheres, plus N, which is the number of moles, times B. B here is called Van der Waal constant, and it is constant for each gas. You will be given for every gas because it is different from real gas. Let's say hydrogen gas, nitrogen gas, oxygen gas, they do vary from gas to gas, and you will be given that. So remember, this equation is for volume correction, taking into account the actual volume occupied by gases, the actual volume occupied by gases. There is also pressure correction, all right, which I want to show you also as well. That at a high temperature, the pressure of gases are nearly identical to those of ideal, but at low temperatures, the pressure of gases are always low. There is the pressure correction as well. This is what I want to show you in terms of pressure. Remember, that was volume. A is called Van der Waals constant, and it is used for pressure correction. P is used for what? Volume correction. So there is B here, which is volume correction. And here A is pressure correction to do that. Now, let's look at xenon, for example, which is a real gas compared to ideal gas equation. For 1 mole at volume for 1 liter, if you look at the temperature, at low temperature, real gas deviate from ideal, but at higher temperature, ideal gas behave as real gases. But at low temperatures, real gases, some of them start turning into liquid, which is no longer a gas. So Van der Waal equation is used to account for Van der Waal equation is used to calculate the pressure of real gases or volume for real gases, and to assume this equation. Remember, this is Van der Waal equation. It's just like real, and it is used to correct for volume and pressure. There is volume correction here. There is the pressure correction here. And it is used for what? For calculating either pressure for real gases or volume forward for real gases, combining the equation to account for molecular volume, which is occupied by molecules over gas, and the intermolecular attraction, that there is force of attraction. We use this. I'll give you in the quiz, and I'll give you also in the exam this equation. Please make sure you know how to use in the calculation. And without much ado, I want to solve one example on for real gases, how we use Van der Waal equation. Let's see how to, just before we do that, how we use or account for this. Is just comparing real gases with ideal, that at higher temperature, at higher pressure, real gases tend to deviate because of intermolecular forces which attract one another. So with this, let's see how you can use understanding on what happened at low temperature and high pressure. Low temperature and high pressure. You see the pressure is increasing. Reading the graph, For CO2 carbon dioxide, the question here is, this is a conceptual question, if you understand real gases versus ideal. The graph shows PV, that is pressure, volume, room temperature, gas, constant temperature ratio, y-axis for carbon dioxide at 3 different temperatures. Rank the curve in order of increasing temperature. How will you know that this is increasing or is decreasing? We have not been given. From the understanding of real gases versus what I gave you earlier on, remember at a low temperature and high pressure, real gases deviate from ideality, right? PV over nRT, let's go back to this. You see this ratio? If here should be 1. For ideal gas, PV over RT is 1. You see it's constant, but they keep on deviating 1. At low pressure, right, or at low temperature, it deviates most. So if I go back to what we looked at earlier on temperature, you see low temperature, it deviates, but high temperature, it behaves as ideal. It is not only for xenon, by the way. It's just for illustration using real gases that at low temperature, even the more we go lower and lower, the more it deviates from the other. So if we increase the temperature here now, going to this equation so that you understand what's going on, I'll say that this is the lowest in terms of temperature because it's deviating. If we took S1 somewhere here, going PV equals to 1, it's deviating. A is deviating from ideality, from ideal gas, followed by this, followed by this. So I'll say that A is the lowest, followed by B, followed by C, and the correct answer is B. Rank according to what? Increasing temperature. This is the lowest because it is deviating more from ideal. Remember, the lower you go in temperature, the more it's deviating from ideal. Read on this section, understand how low temperature and high pressure leads to deviation from ideality for real gases. High temperature and low pressure. So you see here at low pressure, at high pressure, and low temperature, they tend to deviate. Ideal gas, different gases for that. Let's look at one example. I've gone through this adjustment and how the van der Waals equation is used to correct those volume. This slide here, I don't want you to pull your hair, fry your brain trying to memorize the P and A in volume correction for B and pressure correction. This is the pressure correction in the van der Waals equation, and B is the volume correction. Look at where B is. Now, these are just common cases you will encounter in van der Waals equation. You will be given in problem. You have to know how to use them. Let's say a question is based on CO2, for example, right? A will be 3.59 in this equation, and B is will be 0.04274 CO2. If the question is tailored to the specific cars here, you will be given those values. I may even give you in the whole table in the exam and say, hey, this is what you need to know, right? Yours is to plug in the equation. And this is one of the problems I want to use as a learning check to make sure that we understand what is going on. Remember, all right, I will not leave you just away and say, well, I'm assuming side question here may be on Alex. You'll have to refer to the text to get these values right here. If you are not given, please come back to this slide, look at the values you need in calculating either the pressure using Van der Waals equation. The reason why I'm doing this is Van der Waals equation and how do we use. Now, the Van der Waals equation, you see that momentarily so that you understand how to use. The question here is a sample of 1 mole of CO2 gas is confined to a 3.000 liter container. 3 significant figures, by the way. So I know my final answer will have 3 significant figures. Or calculate the pressure at using ideal gas equation and using Van der Waals equation. So A, let's see, A, ideal gas equation. Ideal gas equation, all right, is PV equals nRT. Remember, temperature has to be in Kelvin, so that P equals to nRT over volume. Remember, again, volume has to be in liters, where R is 0.08206. Remember, units is liters times atmospheres over mole times Kelvin. So our temperature has to be in Kelvin, temperature in Kelvin. Since here we are given degrees Celsius, you change to Kelvin, which is 0 plus 273, which is 273. This is what we'll be using in our calculation. Please do not just plug the temperature, which is 0, 0 in this case, or if it was 225, you need to change to Kelvin. So if we plug in there, we have 1 mole, all right, times 0.08206. Let me just, for the sake of space, I'll not put the units, times 273. But remember, you should have the units. It will cancel out over volume, which is 3.00. Just find the numbers, all right? I'm just using the ideal equation. This will be around 7.47 atmospheres. I've used ideal gas equation. Now, part P is use Van der Waals equation to find the pressure. All right. Problems will be on, all right. Problems on Van der Waals will be given the equation, all right. Remember the equation is P, all right, plus N square A over V square, that is volume square. This is Van der Waals equation, times V volume minus NP is equals to nRT. Where R, you know, it is the, we know R 0.08206 liters times atmosphere over mole times Kelvin. That is the universal gas constant. Temperature in Kelvin is 273. You know that. N is 1, which is 1 mole here. We are given 1 mole of CO2. This value, this the gas, and if you look at A and B here, you either have to come to this slide here. You'll be given in the problem, since we are using this, the gas in question is carbon dioxide. A equals to, this is the value for A. For carbon dioxide, 3.0. I'm going to show you my whiteboard in a moment. This is A, and remember the units here. Although B here is what? 0.0427. All right, the units for A is liters times atmosphere over mole square, and this one is liters per mole. Liters per mole T consistent with the units. So with that, we know now, all right, we know now the value for B and the value for A for CO2. If it is ammonia, you will be given. If it is oxygen, if it is any other gas, these two values will be given. Now you have to recall the algebra, how to rearrange the equation. We are looking for what? We are looking for pressure. So we have to have pressure on one side, which means we need to divide. So the question on our making pressure to be the subject of the formula, maybe you should have it at the top here so that I can have that. It's going to be pressure equals to, taking across the equal sign, if I divide that, it will be R N R T over V minus N B minus A N square over V square. This is making pressure the subject of the formula. We want the pressure. The rest, you have to plug in the values. From the units we have here, I'm just going to plug in each value in its respective place. So if I plug in that, 1 mole, that's going to be 1. So 1.00 mole, it's yeah, times 0.0820 to me have the units in there over volume is what? 3 liters minus 1, if you want to, 1 times B. Remember, B is 0.047, so this is 0.04, all right, 27 minus A is 3.59 times 1 square. We only have N stand for the number of moles. Remember, N is number of moles, which is 1. We have 1.00 mole of CO2. So that's why I'm squaring 1 there over volume, which is 3 square. Once you set up everything, plug in the equation, you should have plug in the calculator 7.18 atmospheres. Please express your final answer with the correct number of significant figures. So that's using the ideal gas equation to find the pressure, and using the van der Waals equation. If you compare the two values here, this is 7.47 is because we don't take into account that gas molecule, real gases occupy space. So we have to do what? The volume correction, because they do occupy space there in the volume of a container. Likewise, gas particles too attract one another. So therefore, we need to take into account pressure correction. And with that, you don't end up with the same answer. That marks the end of chapter 6. Please proceed to module 6 on Alex. Complete the assignment before the due date. I'll see you again in chapter 7. Thank you.